Hey guys, I'm really excited to talk to you about some of the work we've been doing on reconfigurable microstrip antennas. Antennas have been reconfigurable, and it's not a new topic. They've been reconfigurable both mechanically and electrically. What we're doing a little bit differently is we're taking our genetic algorithm that we used to solve through simulation, through an open source FEM solver, where we can just give it criteria you want and it creates the geometry for us. We showed a video of it a little bit ago where it's solved for like this antenna here. The video left a lot to be desired. It doesn't really show how powerful it is until you think of, well, what about when you want to get into more complex 3D geometries where you have a lot of points to optimize. Like one of the things that it really shows the power for it is this miniature horn antenna we had to solve for. It's about the size of a WR10 antenna, but it's designed, or it was optimized to operate from 12 to 27 gigahertz with about 8 to 10 dBi of gain. It is dielectrically loaded, so the genetic algorithm optimized for all that, dielectric constant of the material, and then the overall 3D geometry of the antenna. That took about 100 hours to solve, and it created a few terabytes of data, which is why the video left a lot to be desired, because from simulation, it's a really slow process, especially when you're talking about broadband antennas. So we're taking that same principle and we're placing it in the real world where the genetic algorithm is going to be controlling the reconfigurable antenna. But what we did a little bit differently is we also added AI on top of that. So the AI will be creating its data set based off of the evolutionary algorithm, and then we'll show some really cool uses on the spectrum analyzers, how the AI can detect jamming, like electronic jamming, so it could reconfigure itself to operate at different frequencies as a cool show and tell piece. It's not really practical. We'll talk about all that stuff at the end after we do some of these experiments and some of these tests, and we can see how it operates. We'll talk about the practicality of it and where I want to take this for the next steps after this. So the AI is going to be using the evolutionary algorithm to reconfigurable the antenna to create its data set. It'll take the performance criteria. As of right now, for this, we're only going to be looking at a return loss because we can directly read it from our network analyzer, and that's how it's going to be its design criteria. The antenna was designed in a 6-layer board. What you're going to see is each individual layer created on a separate board. We have the main logic board, DC board, and then the antenna board, which is created on some Rogers material. It was really expensive and really slow to get mixed material with Rogers material. Prototypes made. It wasn't really practical, so I went about designing 3 separate boards that we just wire in together. That way I can optimize each separate board. Quick spin, get it within a week instead of 9 to 12 weeks and several $1,000s when you're doing mixed materials. It was designed to be BGA reflown to the DC board. Didn't quite work, so we went a different route. So here's going to be the antenna that we look at. We have the main logic board below, some of the DC breakout board here. It's connected to the actual antenna, which contains all the RF portion, through about 500 pogo pins. There's about 144 individual RF switches, so we needed a lot of pogo pins to make work. So we did run into some issues. Again, I'll talk about all this at the very end. Low frequency, below 4 gigahertz, it doesn't really operate, which it should, because the switch works down to about 10 megahertz. For this geometry, there's 3 grounds to it. There's a true RF ground, true DC ground, and then there's also a floating capacitive ground for the RF switch to have a ground return path, because the DC ground and the RF ground can't be fully connected, or else the RF switches won't work. So there's a floating ground. I think I hypothesized due to the inductance added, also, and it's not high enough capacitance. I'm thinking for the lower frequencies, but due to some of the inductance added, it doesn't really work below 4 gigahertz. Again, for my vision for this, it was good enough to show this, and we're going to keep moving on to the next portion. But so right now, we have our program up. This is where we're going to get the criteria. GPIB is not working because the VNA is not on, but we're going to go ahead and get the VNA on. We're going to get a CALD, and we'll start solving. We're going to solve some different tests. I'll do 2 or 3 quick tests. We'll see. I'll probably do multi-band. Since we know it doesn't work below 4 gigahertz, I'll probably just do like 5, 6.4, and 7.8 there, 1.4 gigahertz bandwidth spacing. So we'll have it solved for that, and then for individuals, so we'll have it be multi-band, those 3 bands, and then we'll also do a broadband for 5 to 8 gigahertz. Let's just go with that since we're already solving that criteria. We know it works really well there, and then from there we'll move on to the spectrum analyzer, and we'll do some testing with the signal generator, and then we'll do some jamming and see how it reacts and how it kind of shows the power of this. So I'm going to go ahead and get everything on CALD, and we'll take it from there. I have the network analyzer on and it's calibrated. You can see why I didn't have it during the intro. It's a little bit loud. The camera's picking up the fan really well. So the genetic algorithm talks to or receives data from the network analyzer over GPIB, and then it sends its next generation, its next configuration over USB. I don't know if I mentioned in the intro, there is 2 separate logic boards, both for transmit and receive. So this antenna can transmit and receive at the same time. You'll see it when we do the next test after we build the data set for the AI right now. So from each pixel to pixel, the most amount of loss it'll experience is about 2 dB, but that can cut down by taking multiple paths. Since we have two logics in there, it's controlling separate switches, so we can create multiple current paths for it through each of the pixels. So that's pretty neat. Just if people are wondering why there's 2 USB cords. There's also going to be a feature about 9.4 gigahertz you'll see above the for the antenna. Even if it's not on, it's there. It comes from the center patch of the pixel. That's how I verified. I took one of the boards and just didn't put any passes on it, just measured return loss, and it was roughly there, almost same magnitude. Obviously with some of the passive components for the switch, it did get a little bit loaded, but we saw the same phenomenon from this. It's that resonance up there by 9.4 gigahertz. You'll see it in the subsequent tests we do. So I typed in the multiband frequency I want. Let's see what the genetic algorithm does or how it solves for it. Let's see what performance it gets. And then after this one, we'll repeat the test for 5 to 8 gigahertz. Again, a band we know it's going to operate really well at based on its current build configuration. Okay, so it's solved. Let's see the frequency points it's solved for. Okay, we gotta wait for my frequency calibration. Okay. So I'm gonna localize it and let's scan. So, well, it's all for 5 gigahertz, but it looks like the main signal is 5.2. 6.4, nice, right where we wanted it to be. And 7.8, perfect. So it did achieve its desired 1.4 gigahertz spacing, or what we wanted. It also solved a little bit higher frequency as well. This could just be a feature down below. 9.8, no, 9.2 gigahertz, okay. But if we load the antennas, like with my hand, we'll see if it's actually radiated or not. Yeah. So some bands a little bit stronger than the others, definitely, but it did solve for the desired frequency point when we're running a multi-band optimization suite for the generic algorithm. Looks like it finished here, so let's see what it solved. So 5 gigahertz is right there. Okay, perfect. 8 gigahertz is up here. So it didn't get quite the whole band. It missed about 400 or 500 megahertz. Now I'm gonna attempt some loading, see if it's actually radiating the whole band. Yeah, it is. It definitely is. It's radiating quite nicely for the whole bandwidth. There is no rejection in here. It takes the average of the bandwidth we're interested in to find. As long as the average is below or below negative 10 dB S11, it'll consider that good for the bandwidth. The algorithm can be further optimized where you have rejection for small signals that creep above a 10 dB or that creep below a 10 dB return loss. We're going to run that 5 to 8 gigahertz bandwidth test again, see if it can solve better this time. Let's see how it did this time. So 5 is good. Creeps up a little bit at 6. So here's the current measurement setup for the next series of tests we're going to do. I have the smart antenna hooked up to the spectrum analyzer. I have a logarithmic Vivaldi antenna hooked up to the bottom signal generator. That's going to be the transmit antenna that's sent to the pixelated smart antenna. And over here we also have a tapered patch antenna that's hooked up to the top signal generator. That's going to be the jamming device that we're going to use to interfere with the transmit signal. Now, I did make a mistake. I had to go back And instead of running for multi-band solving, I had to solve for the individual bands, 5, 6.4, and 7.8 gigahertz. I ran through this test, and then I realized I'm still going to be picking up since we had to solve for multi-band. I had the VNA turned down because we got to pack it up and ship it out for calibration. So it's just, it is what it is. I had to quickly go through it, and I had to learn for 5 gigahertz, 6.4, and 7.8, the same 3 bands we had to solve for in multi-band operation as single bands. So yeah, let's go ahead and get this set up or all powered on and running, and we'll do some tests with it. So we have the antenna powered on. The AI is first data set or data point is 5 gigahertz, so that's what it's set the smart antenna to, as well as the transmit antenna. Now for the first test we're going to do is we're going to see what happens when we put in some interference. So right now I have some copper clad FR4, and if I get into the signal path, so if I just get between the 2 antennas, we can see that nothing really happens. I could get about 15, 20 or so dB of attenuation. We are in the near field, so we are going to be picking up some of the reflected signals off of the conductive base, the aluminum mounting plate that I have this on. So we won't completely block out the signal, but for the most part you can see that we can really drastically change the amount of received power. Okay, so now what I'm going to do is I'm going to get the top signal generator, the one we're going to use for jamming this signal, and we'll see what the AI does then. Okay, so we'll let that align real quick. So we're going to turn on the jamming signal. Okay, I'll turn it back off. Okay, let's see. Okay, I think it's done aligning now. We'll turn on the 5 gigahertz jamming signal. We can see we get a power shift. It shifts up, and then it's shifted up to 6.4 gigahertz. The second data point it has. This is where I initially made the mistake though, because I was wondering if it's still picking up 5.4, because I forgot I had it set for multi-band instead of individual frequency points. So same thing, we'll go ahead and change it to 6.4. Turn on it. Oh, whoops, no, I didn't hit the on button. Turn on. We're going to see power spike. AI is going to switch to 7.8 gigahertz, which is awesome. So that's some of the coolness of this, where you have the AI that's controlling it all. It can sense what's going on. Saw a big power shift. It saw continuous power instead of a little bit of modulated signal that I'm doing. It knows it's jamming. It reconfigures itself to go to a higher frequency point. Great. So that's pretty neat. That's what I want to show here. Some of the neat features it can do. So I just wanted to finish the video off going over some of this, or going over everything we've quickly done. And basically give my thoughts about this. Obviously, since I was the one that worked on this, I really thought it was a cool idea. Reconfigurable antennas, like I said, they're not new, but it was a new way of going about this, where it was really minimal user input. The algorithm solved for everything, And then we were able to showcase it doing something pretty neat, where it was avoiding a jamming signal on the current setup. It was reconfiguring itself. I really want to talk about the practicality of this. Is this super practical? No, not really. Like I said, I think it's really cool, but in the real world we have regulations. We're allotted certain operating bands, so it's not really that useful having something that can configure itself to multiple operating frequencies where you're not allotted those frequencies. Is it neat in like a military standpoint, or electronic warfare? You're avoiding signal jamming, like we showed here. I think it's pretty cool. There's some use to it. Could you avoid doing simulations, and you could do real-world measurements of different designs where you can configure it? Because you have 144, I believe it is, RF switches, and you can create certain geometries. I think it's a stretch. Maybe, I guess. EMC setups where you can set the antenna to work at certain operating frequencies wherever you're testing for any interference, EMI radiation, all that stuff. Again, I think it's all a stretch. I really wanted to showcase this as a neat topic. I've done work on genetic algorithms before, barely any on artificial intelligence. Even this one, it's super simple. It's not really that complex of an AI. It's just basically reading what's going on and loading the next data set. It's not anything massive. But where I want to take this as is not as much the reconfigurable aspect of it, where you can have it operate at different frequency points. It could solve automatically. Where I see this going, or where I want to take this, is into the beam steering. You design a really good antenna to operate at your desired frequency points, and it can control the ground plane to steer the beam. Now, using some of this AI-based evolutionary algorithm, you can have it beam steer and beam track, so mobile cell phones can always have the main beam, the main lobe steering towards the tower. Vehicle-to-vehicle communications, you can have the signal curving, or not curving, changing angles so it follows the car in front of you that's going around the curb. Stuff like that. Cell phone towers where it's maybe sending majority of the signal towards a populous area, and it can change based on the shift in demographic, whatever, sports games, venues. It can send a lot of that power in a particular direction, use beam steering. That's where I want to take this to. This is just a precursor to that. That's where this inevitably is going to go. I just thought this would be a neat way of showcasing everything in a way where we could kind of see it working. Obviously, this is all rushed. All this equipment's going out for Cal this week, so I got to get it packed up and shipped. All the RF equipment's due at once, so we shut down operations from the RF testing to get everything cal'd and get it back. So I just thought I'll quickly do this. But I also want to show some of the stuff we were working on that's pretty neat and new. And I hope you guys really enjoyed this. I appreciate if you stuck through and didn't skip and saw some of the more boring nitty-gritty. Thanks so much.